Already taken.
You're already taking. Oh, great. So what do you think, Chad? How's the clock? All right. So, shall we? Indeed we shall. Let's see. Where's my big fat piece of unbreakable chalk?
Unbreakable.
Well, I could break it, so why would I want to? All right. So, we're going to skip ahead to where it says second derivatives on page 17 of my notes. Before that, there's a listing of product rules, and, well, just know they're there. We talked about first derivative, gradient, right? We can make various sorts of second derivatives that involve vectors. In fact, we could talk about the divergence of the gradient of f. That would be a second derivative we could make that involves vectors. We could talk about the curl of the gradient of f. We could talk about the gradient of the divergence of some vector field v. How much would you pay? Don't answer yet because wait, there's more. You also get the divergence of the curl of v. And if you act now, you can have the curl of v. So count them 5 glorious second derivatives that we could talk about here. And let's say a little bit about each one. First of all, that first one, the divergence of the gradient of f, that is called the Laplacian. That's the Laplacian of f, after good old Pierre Simon did Laplace. And if we just kind of follow what it says there in Cartesian coordinates, div grad f will be d dx x hat plus d dy y hat plus d dz z hat dot df dx x hat plus df dy y hat plus df dz z hat. And so when you do that dot product there, you're going to get d dx of df dx, and x hat dot x hat is 1. So it's going to be, in other words, second partial of f with respect to x, to which we will add the similar term for y, second partial with respect to y, and second partial with respect to z. So the Laplacian of a scalar function, which we call grad squared f when we write it often, the Laplacian is just the sum of the second partial derivatives of the scalar field, excuse me, the scalar field in question. Okay, so that's number 1. Any questions? Onwards and upwards. Number 2, the curl of the gradient of f. That's identically 0. Any gradient, its curl is 0, and we know that since we know that if curl of a vector field is equal to 0, then that means that the line integral around any closed path is equal to 0. And even from first principles, we know that the line integral grad f dot dl around a closed path is 0. Because remember, if you take the gradient of a scalar function, then indeed the line integral between any 2 points is just the function evaluated at the endpoints. Do it around a closed path, and the beginning point and the end point are the same. And so therefore, you get 0. And And then, since we know that good old Stokes theorem, we know that the line integral of what am I trying to say here? And so by Stokes theorem, right. So by Stokes theorem there, if we integrate, if we find the flux, put it this way, if we find the flux of the curl of grad f, over any closed surface, we'll get 0. That means that the curl of the gradient has to be 0. Or just in general, what it comes down to is that if a vector field has line integral around any closed path is 0, we know that an equivalent condition is that the curl of that vector field is 0. Grad f has that condition, therefore curl grad f must be equal to 0. So the curl of any gradient is equal to 0. And you can also just prove that directly by finding all the partial derivatives, and you'll see, hey, mass cancellation, everything goes away. It's like 0. Okay, any questions? All right, so number 3. Not seen often in physics, although we will see that it does show up in one context. We'll see that for number 5, it's going to involve number 3. Curl is grad div minus del squared, we shall discover. Except C5. Doesn't show up often in physics, but we are actually going to see that it shows up when you're evaluating curl. 4. The divergence of a curl of any vector field is always equal to 0. As you will show, only if you're putting this in your notes, as I will show, not me, but you will show this.
I'm not ready now. Hey. They use something with a K and put a heart over an I. K-O-R-I.
Okay.
Heart.
Wow. Okay.
Well, that is just generic.
It's just generic. Yeah.
Corey, do you remember that? You don't like that?
Yes.
Really? Wow. I'll have to find out more about that sometime. Alrighty then. Was this like if Corey were a girl kind of thing here? Or,
Basically.
yeah. You do strike me as kind of feminine.
It must be
All
there.
right. So, number 5. Number 5 is a fun one. A vector identity applies here. As I mentioned before, curl V is equal to rad div V minus del squared V. Now we've defined the Laplacian for a scalar function in Cartesian coordinates, it works out that the thing that you need in order to make this identity true is to define grad squared v as just being the sum of the Laplacians of the individual components. So in other words, it's grad squared of v sub x, the Laplacian of v sub x, the x component of our vector field v, times x hat, plus the Laplacian of its y component times y hat, plus the Laplacian of its z component times z hat. Now, when we get to curvilinear coordinates, so for our purposes that'll be cylindrical coordinates or spherical coordinates, then that doesn't work. In other words, we go to spherical coordinates. And I'm just going to assume that you've seen some spherical coordinates before, so even though we haven't talked about it yet, I'll still say this. Grad squared v, for example, does not equal the Laplacian of v sub r times r hat plus the Laplacian of v sub phi times phi hat plus the Laplacian of v sub theta times theta hat. Doesn't work. And in fact, if you want to get the right expression, the way to do it really is just you define, in general, the Laplacian of a vector field to be equal to curl v. Let me get this right. No. Grad div v minus curl v. So in other words, just solve that thing for grad squared v. So that's just defined to be grad div v minus curl v. And anyway, this vector identity actually does turn out to be useful. It's something that you do, in fact, have occasion to apply sometimes. Okay, any questions? Now, we will find that the Laplacian is our friend. It's going to bring us much happiness and joy in the months to come. Because in electrostatics, you may recall that the electric field is the gradient of a scalar potential. So in other words, the potential V exists in electrostatics such that E is minus the gradient of that potential. And we know that Gauss's law in differential form, so
Gauss's law
is that the divergence of E is equal to rho over epsilon naught. So the divergence of the gradient of V, which is grad squared V, is equal to minus rho over epsilon naught. And this is known as Poisson's equation. And what it's telling you is that if you know the charge density everywhere, then this is a partial differential equation that allows you to determine the electric potential everywhere. And then you can take its gradient to find the electric field everywhere. So this is saying that in electrostatics, knowing the charge distribution lets you find the electric field everywhere, which we already know. This is equivalent to Coulomb's law. You can also find the electric field using Coulomb's law. But it's often a lot easier and more convenient to solve this equation than it is to directly solve using Coulomb's law and integrating over the charge distribution. As we'll see, there are nice tricks you can use to allow you to make approximate solutions of Poisson's equation, for example, on a computer, that is easier than integrating over the charge distribution using Coulomb's law in order to find the electric field. So the Laplacian is our friend. And no, it's not true that you should be saying that with friends like that he needs enemies. It really is our friend. Okay, any questions? Two theorems that are of great significance, and your book gives them the clever names Theorem 1 and Theorem 2. It's like thing 1 and thing 2. So, Theorem 1, this is on page 53 of your book, says the following conditions are all equivalent. A, the curl of B is equal to 0 everywhere. And such a vector field is called irrotational. Because remember that if we think in terms of fluid velocities, if there is a curl, if there is a line integral of B that isn't 0 around closed paths, that means in general terms you got a situation where a little paddle wheel would turn because you have that overall there is rotation in the velocity field. The fluid will set things spinning because, for example, if B was a bunch of circles, if the field lines were a bunch of circles, if the field lines of B were a bunch of circles, drop a paddle wheel in there and it'll start spinning around in the direction that the fluid is spinning. So, if curl B is 0, B is irrotational, little paddle wheels won't tend to rotate if you drop them in the fluid, if it's a fluid that you're talking about. A lot of the physics applications of vector calculus were first developed in fluid dynamics, and then that gives us terminology that's sort of appropriate for fluid mechanics that shows up even when we're talking about, say, electrodynamics. If the curl of B is 0 everywhere, then it's also true that the line integral of B dot dl between any 2 points is independent of path. And vice versa. If the line integral is independent of path, curl B is 0. Again, the following conditions are all equivalent. If any one of them holds, all the other ones do too, is what I mean by that. If any one of those conditions is true, so too are all of the others in a harmonious union. Similarly, the line integral around any closed path is equal to 0. And finally, D V can be expressed as a gradient of some scalar function. There is a scalar function such that V is its gradient. F is not unique. We can add any constant to it. Maybe we should call it a constant function. In other words, a function which is the same everywhere in space. Because the gradient of a constant is, of course, 0. The derivative of a constant is equal to 0. So the gradient's just 3 derivatives, and they're all going to be 0. So whatever f is, you pick an f that works, that v is its gradient. I can say let's add 37.426663 to it, and my new gradient will work just as well as yours. Thank you very much. Okay? And that's the sort of thing that you're familiar with. That's basically the notion that the electric potential is only defined up to an arbitrary scalar. Similarly, the potential energy, which is the charge times the potential, is also only defined up to an arbitrary constant, because what matters are differences between potential energies, not the actual potential energies themselves. Or when you're finding the electric field of a gradient involves taking differences in the limit as you go to zero separation. Since only differences matter, adding an arbitrary constant to the scalar doesn't change anything. Okay? Then there's theorem 2. On page 54 of your text, the following conditions are all equivalent. And you ought to burn these into your brain. Every physicist should, just like as soon as you hear one of these things, the other ones all come to mind. You're knee jerks and you just know. All those things are in there. So, A, the divergence of B is equal to 0 everywhere. In that case, we say B is solenoidal. The word of the day is solenoidal. Why would we say solenoidal for that? What's a solenoid? Yeah, it's a a wire thingy like that. You can wrap a bunch of wires around like that, and pass a current through a solenoid, and it creates a magnetic field, right? And what's the divergence of the magnetic field? 0, because there's no magnetic monopoles, no charges, so field lines of the magnetic field are always closed, so the flux through any surface is always 0, there's always flux in and flux out of any surface. So the reason we call it solenoidal is because it's B field-like is what it comes down to. It's like the field of a solenoid, and so we call it solenoidal. So here's a case where E and M got the privilege of naming the type of field, not fluid mechanics. So if div B is 0 everywhere, then it follows that the flux through any surface is going to be the same for all surfaces spanning or bordered by a given curve, I'll say. So B dot dA is the same for all surfaces. And by the way, I'll point out, when I'm talking about this, I'm talking about open surfaces here. If I've got a curve and you think of that curve as like a loop of wire, and you blow a bubble with it, and so you dip it in the soap solution and you blow a bubble, thereby making an open surface. You can stick your hand inside of it without going through soap. You can stick your hand inside the loop and not go through any soap. It's an open surface. That's what I'm talking about here. For all open surfaces, bordered by a given curve, a given closed curve. You don't make very good bubbles if your wire loop isn't actually a loop. You have to have a wire loop in order to blow soap bubbles. So, if B is true, then A is true. If A is true, then B is true. And if those are true, then so too is C, which says that flux of V through any closed surface is 0. And here we should comment on a similarity between conditions B and C for both theorem 1 and theorem 2 here. Namely, for theorem 1, remember if we've got two endpoints, we said that if the line integral is independent of path, it follows that the line integral around any closed path is 0. The reason being, he said, trying to make these diagrams identical except for the directions of the arrows on the turn path. So, okay, not perfect, but in any case, the reason being that if I make a closed path, then I have to traverse one of them in the opposite direction that I traversed the first one. So if these two are equal to each other, well, when I reverse the direction of the arrow in a line integral, I change the sign of the result. So if these two are equal to one another, then these two are equal and opposite. So my closed path gives me 0, right? Everybody got that down, right? That should be deeply intuitive to you if all is going well. And if it's not, be sure you achieve that happy state now, and then you will have joy to go with it. Now consider some closed curve and some surface, which that curve is the border of. And if it's true that for open surface number 1, the one on the top there, and open surface number 2, so in other words, consider the two separately. If the flux through both of those is the same, and if I'm going to say that, I have to make a consistent definition of outward unit normal there. So, I don't know how well I can draw this, but in other words, what I would want is that if I'm choosing the outward normal to be in some sense upwards for the first surface, it also has to be upwards for the second surface. You could do a right-hand rule kind of thing in terms of, it's really topology here that we're talking about. But in other words, if I decide I'm going to go around this curve in that direction, then I want to choose my outward normal with a right-hand rule. That's the rule for using Stokes' theorem. You have to make the outward normals be related to the direction of traversing the curve by a right-hand rule like that. So both these surfaces will have the normal vectors pointing upwards. Those two fluxes through those surfaces are equal. If condition B holds. That's not always true for an arbitrary vector field, but if condition B holds, those two fluxes are equal to one another. If we assume that's true, for the closed surface, which is the union of 1 and 2, the net flux must then be 0. Why? Why, if these two fluxes are equal to one another, is the net flux through the closed surface 0?
Flux is equal.
Yeah, or we have to be a little careful. What direction does n hat point for the closed surface on surface number 2 here? Does it point in, well, careful. That if I have a closed surface, n hat is going to be the outward normal. When we talk about fluxes for open surfaces, n hat is arbitrary. You just have to pick it and be happy, make your choice. Unless you're talking about Stokes' theorem, in which case you relate what you call the outward normal to the direction that you're traversing the border curve. So if I want to use Stokes' theorem here, if I'm going to trace the border curve like this, then I make n hat be up in both cases. I use a right-hand rule. That's weird looking. Okay? But for the closed surface, which is their union, n hat's always the outward normal. Which direction does n hat point if we're talking about the outward normal for the closed surface, which is their union? Does it point upwards or does it point downwards? It points downwards, right? So the reason that this is true is because n hat on surface 2 for the union points in the opposite direction as it does for when we only look at 2 as an open surface there. So making a closed surface forces us to switch the direction of n hat for one of our 2 open surfaces. So in other words, for the closed surface, then the flux through this portion of it becomes minus what it was before. So if these 2 fluxes are equal to one another when you consider them as open surfaces, for the whole closed surface, you flip the sign of one of the 2, and so they add up to 0. And that's, in other words, we've kind of jumped a dimension here. When we find the line integral around a closed path, then we had to flip the direction of one of the paths, and that changed the sign of the line integral. When we find the flux integral, the 2-dimensional flux integral through a closed surface, we had to flip the sign of the flux because we flipped the sign of n hat for one of the surfaces. And so that causes equal and opposite fluxes for the entire closed surface, and so the total flux is 0. So that's why B and C are equivalent to one another, because when you form a closed surface from the union of 2 open surfaces, then that flips the definition of n hat for one of those 2 open surfaces, which then flips the sign of the flux through that open surface, which then makes the flux through the whole surface, the whole closed surface, equal to 0. Okay, does that make sense? Or should I say it again in a different way, or what? Okay, so be sure you see the similarity here. Path independence implies integral around a closed path is 0 because you have to reverse the direction of one of those 2 paths for the closed path. Surface independence for the flux means if you make a closed surface by putting 2 together, you have to flip the sign of n hat. Just here you're flipping the sign of dl. Well, flip direction of dl. On the return path, as it were. Here, flip the direction of n hat on one of the 2 surfaces. Is that the smile of happiness, or? I just don't see the kind of happy expressions that I'm looking for.
It's a smile of joy instead.
What's that?
It's a smile of joy.
The smile of joy instead. Yeah, okay, right. Happiness, joy, yeah. But of course, what I'm really hoping for is a combination, a union of happiness and joy. And in this case, it's not cancel. No, it's no cancellation. It works differently. No.
They are.
It's reinforcing. They are in phase.
I feel neutral.
You feel neutral? I guess that's better than feeling bad.
I'm feeling godless.
Okay? But seriously, if it's not making sense to you, speak up. You know, right? There's always two situations. You know, a lack of questions because it's crystal clear, and a lack of questions because you're thinking, what the hell? You know, right? So, and I'm fearful that I'm seeing some what the hell here. So, if so, somebody say, what the hell? All right, nobody's saying it.
Want me to say, I mean, I'll say it if you want me to say it.
Well, no, I only want you to say it if you're actually feeling it.
Just ask Chad.
Ask
I
who?
think I hear him
Chad.
saying,
You think you
what the
hear
hell?
Chad, you think what the hell? Crystal clear. Okay, good. No, he's fine with it, actually. Yep. You're right. It would be cute. Yeah, let's do that. Little puppy inside the surface.
Oh.
Yeah.
You put it upside down, puppy in the
Yeah.
Is it inside or is it walking on?
No, he's inside the surface apparently.
I can't tell.
No, he is inside, actually. Right. Well, here, you know, if we do some shading.
Oh no, it's a puppy in a bubble.
Puppy in a bubble, that's right. The poor thing's immune system never developed. And so,
It'd be so sad if we were puppy that little bit bubble.
yeah, that's right.
That would be the ultimate when you're a puppy universe.
You have to.
It could be like a little hamster ball and it could like run everywhere.
That's true, right? Yeah, hamster in a bubble would be fine.
But then if it peed in there, it would end up. That'd be awesome.
Puppy in a bubble. That's good.
I love our name. Puppy in a bubble.
And our sines and cosines aren't bad. I turned around in time.
I don't. It's because I saw
Like
the words.
loudly,
It's because beautiful.
Will is so confused, he's like,
Well, it wasn't the process of thinking, how could I be on?
Curvilinear coordinates.
It's because I saw that word funny.
That's made up.
What do they do? Curvilinear, no, curvilinear coordinates.
It's.
It does seem strange though, doesn't it? Curvilinear.
Yeah.
It's like hot and
Yeah.
cold, you know?
Hot
for words.
Right. Okay, right. Things that aren't straight. Let's start with spherical, polar coordinates. So, it's really, you don't really need X, Y, Z axes sticking around here, but suppose you have them anyway, then we can say by convention that the Z axis is the polar axis. It doesn't have to be, but we typically do that. And so we've got us a point in space, and instead of specifying its location by giving X, Y, and Z, instead, we specify its location by giving R, theta, and phi. And the way those are defined is that theta is the angle between the line joining the point to the origin and the z-axis. So theta is the so-called polar angle. If you're a mathematician, unfortunately, you call that phi, just to make it really confusing in going between math papers and physics papers, or math classes and physics classes. However, as physics majors, I expect for you to join my party and consider this to be the self-respecting way to define these coordinates. Phi is the angle between the projection of the line joining the origin to the point onto the xy plane and the x-axis. Or in other words, it's the angle pictured. This is one of those pictures is worth, I don't know, 14 words or something like that. And so if we want to talk about something like this parallel. Oh no, actually, it's, yeah, this, okay, whatever, I'm not even going to try to draw this. No, okay. Don't you like decisiveness? Don't roll your eyes back there.
I already did.
Yeah, I know you did. No. All right. Anyway, x is equal to r sine theta cos phi. Y is equal to r sine, oh, and r, by the way, r is the distance of the point from the origin, the radial coordinate. Y is r sine theta sine phi. Z is r cos theta. And you ought to be able to see those things readily. In other words, if I project onto the z-axis, r, I'm just going to get a right triangle. So, even though it doesn't look like it in the picture, but that's just because things are sticking out of the board, that's actually a right angle right there. We're just projecting projecting r onto the z-axis here. The line from the origin to the point onto the z-axis. Here's the angle theta. We've got a right triangle, and so we've got the hypotenuse is r, and then therefore that projection onto the z-axis is r times the cosine of theta. Does that make sense? No? Okay.
Okay.
You're kidding? Oh, okay. Is everybody happy then? Happiness? Do we have joy in addition to happiness? Yes? Good. Okay, wonderful. And then to get x and y, note that if this is theta, so too is this theta, and here we've got a right angle down there, and so now we've got a right triangle whose hypotenuse is r, here's the angle theta, so the projection onto the xy plane is equal to r sine theta, and then I take that projection r sine theta onto the x-axis. Well, this time we've got a right triangle, and we've got this angle phi, so the hypotenuse is r sine theta, projected along the x-axis is r sine theta cosine phi. Whereas, if I want to find the y-coordinate, now we've got the angle opposite phi in the right triangle, whose hypotenuse is r sine theta, so it's r sine theta sine phi for the y-coordinate. So, if you know r, theta, and phi, you can figure out what x, y, and z are. Conversely, suppose you know x, y, and z, and you want to figure out what r, theta, and phi are. You invert these relations and find that r is x squared plus y squared plus z squared to the 1/2 power y. Why is that following? Yeah, that's just the Pythagorean theorem generalized to 3 dimensions. That's just the distance formula. Right? Distance formula between 2 points is the square root of the sum of the squares of all the coordinate differences. One of the coordinates is the origin here, 0, 0, 0. So distance from the origin is just, yes?
Where is he?
Thank you. Yes.
I don't want Chad to get it wrong.
Yeah, that's right. Yes. So Chad, yes, that is very nice of Steph. So anyway, right, I had to square z there. Notice also, if I do add and square these things, I do in fact get r squared, right? In other words, x squared is r squared sine squared theta cosine squared phi, y squared is r squared sine squared theta sine squared phi, z squared is r squared cosine squared theta. So these two terms are going to give you r squared sine squared theta times cosine squared phi plus sine squared phi. Well, what's cosine squared phi plus sine squared phi? It's equal to 1, yes, and so therefore you just get r squared sine squared theta plus r squared cosine squared theta. Oh, but sine squared theta plus cosine squared theta is also equal to 1, so you just get r squared for x squared plus y squared plus z squared.
Wow.
So, gee, you know, that ought to work, and sure enough it does. If it didn't, we'd all go home. All right.
You didn't turn out that.
Right. Phi is equal to the inverse tangent of y over x. And here you have to worry about the fact that inverse trig functions are multi-valued. And so you have to be careful to figure out which quadrant you're in if you're going to figure out what phi is. Because your calculator won't always give you the right answer. It might be in the wrong quadrant. But that's easy enough to see. You can either just look directly at this right triangle right here and say tan phi is y divided by x, and there you go. Or you can just divide y over x, and the r sine thetas will cancel out. You'll get sine phi over cosine phi, which is tan phi. So tan phi is y over x, or in other words, phi is inverse tangent of y over x. And then theta is equal to the inverse cosine of c over r, but we want everything in Cartesian coordinates, and since r is the square root of x squared plus y squared plus z to the 1/2 squared. Okay, I was just pointing stuff to speak up again. X squared plus y squared plus z squared to the 1/2. Well, there's theta. So now if you tell me x, y, and z, I'll tell you r theta and phi as well. Okay, that sounds like a good point to take a break. Okay, so we need us some unit vectors to go along with our curvilinear coordinates. And just like in Cartesian coordinates, x hat points in the direction that x is increasing, and y hat points in the direction that y is increasing fastest, and z hat points in the direction that z is increasing fastest. We make same definitions here. So r hat is the unit vector in the outwards direction from the origin, the direction in which r, coordinate r, is increasing fastest. Theta hat is obtained by making a unit vector in the direction in which theta is increasing fastest. So if my if my shoulder is the origin and my fingertip is the point in question, then, you know, angle from straight up is theta. It's like, I don't know, little teeny pot. But anyway, now my finger is pointing in the theta hat direction. So r hat, theta hat, phi hat. You know, because phi hat means pointing in the direction phi is increasing. So wow, I'm doing a pirouette here. No, I'm busy. All right. But anyway, phi hat then, if I can draw it here, let's see, in this picture, yeah, it's kind of ambiguous as to whether what side of r hat is, because I'll just draw it like this. So here is phi hat, and just realize, you know, it's 3 dimensions here. So phi hat is really kind of almost going into the board here, okay? So r hat, theta hat, phi hat, and because you are desirous of happiness and joy, I, the student, will show in my homework that r hat is equal to sine theta sine phi, cos phi, sine theta cos phi times x hat. In other words, we're trying to relate the unit vectors of spherical coordinates to the unit vectors of polar coordinates, plus sine theta sine phi y hat plus cosine theta z hat. That one's actually pretty easy because notice that r hat is equal to the position vector r divided by its magnitude r. So in other words, it's equal to x hat plus y hat plus z hat divided by r. And I leave it to you to see that that quite immediately leads to that expression. It's a little trickier to do theta hat and phi hat. Theta hat is cosine theta cosine phi x hat plus cosine theta sine phi y hat minus sine theta z hat, and phi hat is equal to minus sine phi x hat plus cosine phi y hat. Note that phi hat clearly doesn't have a z component because phi hat, being in the direction that phi is increasing most rapidly, is parallel to the xy plane here, right? R hat, theta hat, phi hat, the xy plane. If I'm the z-axis and the floor is the xy plane, phi hat is pointing like that, parallel to the floor. Okay, questions? Okay. Now, just like in Cartesian coordinates, we can express any vector as a sum of the three of components along the three unit vectors. And so we can say that any vector A is equal to A sub r times r hat plus A sub theta times theta hat plus A sub phi times phi hat. Notice that the position vector is always r is equal to r hat like that. That's always true. But in general, a vector that isn't the position vector can have theta hat and phi hat components. The position vector itself points only radially, and so it's always its magnitude times the unit vector in its direction, r hat. Unlike the thing that makes spherical coordinates and polar, cylindrical coordinates a bit trickier is, unlike x hat, y hat, and z hat, and I had a little mistake in my notes here, and then to say they differ from point to point, where they refers to r hat, theta hat, phi hat. The vectors r hat, theta hat, and phi hat differ from point to point. Right? I mean, you can see that. In other words, again, if my shoulder is the origin and my finger here is r hat, as I move around pointing to different locations, r hat is moving around too, and so is theta hat, and so is phi hat, something like that. You know, the whole triple of vectors is moving around as you go to different locations. So the unit vectors aren't constant, and that means two things. So we can't just add components of vectors defined at different points. Better switch to Cartesian coordinates, add them, and then switch back to polar coordinates if you want to do that. Can't just add components of vectors that defined at different points. And when obtaining vector derivatives, like for example, say grad square, etc., the unit vectors also need to be differentiated. You have to find the derivatives of the unit vectors. And if you do kind of ordinary vector calculus, that's a real pain in the neck. It turns out that if you do tensor calculus like you do in special relativity, there are more, general relativity, there are actually more straightforward ways to obtain expressions like the Laplacian and so forth, but that would take us way out of where we want to be here. I'd like to be there, but we can't go there because we're in E&M, not general relativity, which is kind of sad. But, well, I mean, I love E&M, but I mean, general relativity, it's even funner.
Sorry, guys.
Yes,
I
all
didn't to
right.
be here.
We're being shortchanged on our happiness and joy.
Yeah, it's true. General relativity, I mean, there we're talking like ecstasy. Those are your happiness and joy.
Dr. Martin, what did you
What's that?
Nothing.
Rachel, what did he say?
I actually don't know.
Yeah, that's what
I
I
do.
said.
I
You'll
can
find out.
review the tape. That's right. Yes. Plus, I've got a mold back here.
I didn't hear it.
You didn't hear it? All right.
I
you're
didn't
gonna
hear
have to
either.
review
What's
the
the heck
tape.
answer?
What's the time on the
Yes.
tape right now?
As in the drug.
About 9:30.
About nine
9 minutes, 30 seconds.
About 9 minutes, 30 seconds. Okay.
Who
So.
remembers this?
Okay. What about the line element? In other words, in Cartesian coordinates, EL is dxx hat plus dyy hat plus dcz hat. But line, what are you laughing at, huh?
William just turned around and looked at me and then turned back.
I saw smirking back there. I'm paranoid now.
I don't know,
You
you're
were
just like,
talking about.
Randomly start laughing.
That's right. Yes. I thought maybe I write like liniment or something like that, but no. Okay.
Oh, it'll happen.
Okay.
But next time you do, I'll just laugh hysterically.
The line element is drr hat plus rd theta theta hat plus r sine theta dv hat, which is something that you shouldn't need to memorize. You should be able to visualize this and figure it out. Okay. So the idea is that, and I'm just going to draw this as 3 separate pictures because it's
You add another fee to the end of that.
where.
Your feet have, you don't have deep feet.
Oh.
You need a deep fee in there.
You're just trying to save time.
Yeah. R sine theta dp. Yes. Thank you. That's better.
It was just you're saying it out loud that it kind of
Right.
like.
It's actually, well, what threw me there is I have that in my notes too. I'm
Oh,
missing
do you?
fee hat. Yeah,
Oh,
I
you
meant
did?
that to be there. It's below, but I forgot to put it right there. So I was
I was
just
looking
blindly
below.
following my notes. I am a robot, and so I didn't catch that there. But I'm glad you did.
I was looking below, so I didn't even catch that
Excellent.
it was.
All right. So the idea is that if I make a small displacement only in the radial direction, I'd be going a distance dr in the r hat direction. A small little radial displacement would be dr in the r hat direction, whereas a small displacement in the theta hat direction would entail leaving r the same, staying the same distance from the origin, but moving through a little angle d theta change d theta in the polar angle. So if I go like that, my arm is of length r, and I'm moving an angle d theta. So I'm moving a little distance which is r d theta in the theta hat direction, if I only move in the theta hat direction, so that r stays the same and phi stays the same, then I'm moving r d theta from the small angle formula, right? R d theta is the length of that little arc there, and it's really a straight line, but in the limit as d theta goes to 0, then the length of that little straight line becomes the same as the length of a little arc would be, r d theta. And similarly, if I made a little displacement only in the phi direction, then what I'll be doing in such a case is keeping r and theta the same and changing the azimuthal angle, it's called. We'll change the azimuthal angle by an amount d phi. And so I will then be a distance r sine theta from the z-axis. So I'll be moving on a little arc, a little arc of a circle of radius r sine theta through an angle d phi. And in the limit as d phi goes to 0, that little arc of a circle is the little straight line displacement that I've made. So I'm moving a distance r sine theta for the radius times d phi for the angle times phi hat. So that, if I displace in all three directions, the radial component will be dr, the polar component will be r d theta, and the azimuthal component will be r sine theta d phi. Hence, that's what the line element is in spherical coordinates. If I want the volume element, well then, I draw a little r-par. So I imagine a little r-par, which will have, in the limit as all the displacements go to 0, straight sides. For a finite volume, it's not quite straight sides, but as the displacements all go to 0, it becomes truly an r-par. And so it'll have thickness dr in the radial direction, and it will have thickness r d theta in the polar direction, and it will have thickness r sine theta d phi in the azimuthal direction. In other words, the line element displacements are the sides of my little r-par there. If I make a little cube, or in general a little r-par, at some point in space, by going outwards a little distance dr, azimuthally a little distance r sine theta d phi, polarly a little distance r d theta, I'll have made a cute little r-par whose volume is equal to dr times r d theta times r sine theta d phi. Or in other words, r squared sine theta dr d theta d phi. That's the volume element in spherical coordinates. I remember at the University of Chicago, when I was a graduate student, there was a math student taking the physics class, and when I showed this, he was amazed because nobody in his math classes had ever told him that. All he knew was you're supposed to find the determinant of the Jacobian, right? That matrix of partial derivatives in order to convert to dx, dy, dz to the volume element in terms of dr, d theta, d phi. And so he'd never been shown this picture that lets you intuitively see that that's the volume element. And so I gave him a little talk about, physicists think more intuitively, and you silly math people should draw pictures in addition to finding Jacobians. I mean, finding Jacobians is a wonderful thing and all that. That's how you rigorously prove it. But, I mean, come on, people. So that's the volume element. And so if we want to do a volume integral, we use that as the volume element. So in general, if we wanted to integrate over some sphere, and it doesn't have to be a sphere, it could be some more general shape thingy, but if we have some function, rho of r, theta, and phi written in spherical coordinates, over a sphere of radius r, then what we would do is we would say we're going to integrate from r equals 0 to the radius of the sphere. Theta is equal to 0 to pi, because note that that's the range that the polar angle goes over, 0 along the z-axis down to pi in the minus z direction. You don't move around because if I'm talking about this right here, well, I could just go from here to here. So phi is always less than pi. I'm sorry, theta is always less than pi. Theta is always less than pi. Theta is 0 to pi. And phi, on the other hand, goes from 0 to 2 pi of integrand, rho of r theta phi, times volume element, r squared sine theta, dr d theta, d phi. Example, what's the volume of a sphere? Well, that's easy. If you ever forget the formula for the volume of a sphere, just draw this cute little r part, and then integrate it, and you'll get the formula. So, in other words, here we're just integrating d tau to get the total volume. So that would be the integral from r equal to 0 to r of r squared dr. Because remember, a multiple integral can be written as a product of 3 integrals if you can factor the integral. So you can pull, if you can bring everything into separate r, theta, and phi terms, you can just write as the product of the 3 integrals. So r squared dr, theta going from 0 to pi, of sine theta d theta, and phi going from 0 to 2 pi of d phi. And so that'll be 1/3 r cubed, integrated, evaluated between 0 and r, minus cosine theta, integrated between 0 and pi, and phi, evaluated between 0 and 2 pi. So you get 1/3 r cubed times 2 pi, or in other words, miracle of miracles, 4/3 pi r cubed for the volume of your sphere. So I mean, that's where it comes from, basically. But that's actually kind of a silly way to do this one. You really could have just turned it into an integral on r, because theta and phi, the integrand has no theta and phi dependence overall, right? In other words, I'm sorry, that's not true, but you can still just do it only, you can make, yeah, the integrand has no r, never mind. Anyway, you can do it as an integral on r, and it'd be obvious, so I'm going to trip myself up. So, often we have problems that have symmetry. They might have azimuthal symmetry or polar symmetry, or sometimes both, where the function only depends on r that you're trying to integrate. If we've got azimuthal symmetry, or in other words, the integrand does not depend on phi, that's azimuthal symmetry. If whatever you're integrating doesn't depend on the azimuthal angle phi, which is quite common, it might only depend on r and theta, then we can just integrate over phi to get 2 pi. And for the volume element, d tau is equal to 2 pi times r squared sine theta dr d theta. In other words, we kind of pre-integrate on phi and just go right away to 2 pi r squared sine theta dr d theta for the volume element in that case. And the idea is we take our r par, remember the r par that we drew before, so imagine that my fingers here are this r par, that cute little cubey thing, and you just sweep it around the z-axis, sweep it around all the azimuthal angle to create a little thin cylindrical ring, and we want the volume of that cylindrical ring as our volume element. I got myself dizzy, I'm very prone to that. Right? You guys know the story about my sisters and why I get very dizzy now when I do that? You do, yeah.
I know.
You don't, okay. My grandma used to, when I was a kid, of course, kids like to go wee, wee, wee over to, and my grandma would be like, "Mommy, you're making me sick." And I never understood it. And then one fateful day, when I was 12, and my younger sister was 4, and my second youngest sister was 6, we all had a nice, delicious, large spaghetti dinner. And then the two of them got on their sit and spin. You guys know what a sit and spin is? It's a little, yeah, it's like a little platform that rotates, and there's a wheel in the center, and you grab it, and you sit and spin. And they got on their sit and spin rapidly, and one of them produced projectile vomit. Upon seeing that, the other one immediately followed suit. And I witnessed the entire sad affair. And
immediately upon seeing it.
and I did not. I kept my cookies. But ever since that time, spinning around has made me sick and queasy. And I understand grandma now. And so, however, following the principle that there's no sacrifice too great in the name of science, I will nevertheless sweep out little cylindrical rings and so forth. So I'm really sacrificing when I do the angular momentum conservation demonstration. Yeah, and you guys are kind of spinning still a little bit. But anyway, so what we've created then is, in that case for the volume element, a little cylindrical ring, and the radius of it is equal to r sine theta, right? In other words, the z-axis would be sitting through here, and its radius is r sine theta away from the z-axis. And its thickness will be r d theta in the polar direction. So there's my little d theta right there. So I've got a ring who's got a circumference of r sine theta, a thickness in the outwards from the z-axis direction of dr. No, it's not dr. What is it? It's no. I'm sorry. Oops. Wait, I'm messing myself up here. This is. Let's see. This is. What did I do here?
Yeah.
I have to flip them. Yeah, right. So this is dr, and this is equal to r d theta. Right. Okay. And so the volume of that thing is going to be, well, the volume of a cylindrical shell is the area of the base times the height of the shell. So here we've got the same sort of thing. So we've got r squared sine theta times dr times d theta for the volume of the whole thing there. And I'm still looking at that and not happy. What am I doing here? Let's see. Oh, you know what it is no, this, I think I might, yeah, no, that is
That's right.
Is it?
Yeah. Because if that's d theta there,
Wait a minute. RD theta, yeah, that's, yeah, right, yeah, okay, I'm happy again now, yeah, RD theta, okay, my notes are correct, yeah, RD theta and dr, right, so the thickness, so the area of this top surface here is 2 pi r sine theta, the circumference, times its thickness, r d theta. And then to get the total volume, you have to multiply by the height dr. So 2 pi r sine theta times r d theta times dr gives you the volume. 2 pi r squared sine theta dr d theta. So that's your volume element to use if you've got azimuthal symmetry. But often we've got a situation where the integrand depends only on r. Then we just want to use a spherical shell. So in that case, our volume element just becomes a spherical shell of thickness dr and radius r. And the volume of this spherical shell, in the limit as the thickness goes to 0, will be its surface area times its thickness. That's an approximation, but as the thickness goes to 0, the approximation becomes exact. So d tau is equal to area times thickness. Or in other words, 4 pi r squared dr. So really, certainly for a sphere, the integrand doesn't depend on r or theta or phi, so we could just say then that we've got a situation where we could find it by integrating a spherical shell's volume. So the volume of a sphere then would just be 0 to r of 4 pi r squared dr, which immediately produces 4/3 pi r cubed when you do the integral. Okay, so I've got an example in the notes of finding the charge inside a hemisphere of radius r centered on the z-axis and lying about the xy plane if rho of r and theta is equal to r cos theta. So that'd be a case where the integrand didn't depend on phi. And I do the integral there and get the result pi r to the 4th over 4. I'll let you work through that. But in the interest of keeping on, let's talk about the vector derivatives expressed in spherical coordinates. We'll list them here. The gradient of some scalar f is partial of f with respect to r times r hat plus 1 over r times the partial of f with respect to theta hat plus 1 over r sine theta times the partial of f with respect to phi times phi hat. Now, the gradient is easy to whip off without having to look at a table or whatever. Because notice that essentially all we're doing here is dividing by the line element for each component. So it's just like in Cartesian coordinates. To find the gradient, you find the change in f over the change in the x direction, x hat, plus the change in f over the change in the y direction, y hat, plus the change in f over the change in the z direction, z hat. We're doing the same thing here, kind of roughly speaking, because remember the line element has components of dr r hat plus r d theta theta hat plus r sine theta d phi hat. So it looks sort of like you're taking df over dr for the r hat component plus df over r d theta for the theta hat component, and df over r sine theta d phi for the phi hat component. So for finding the components of the gradient, you just divide by the corresponding components of the line element. So as long as you remember what the line element is, or derive it if you forget, then you can easily write down the expression for the gradient in your curvilinear coordinates. On the other hand, when you talk about things like divergence, well then kind of all hell breaks loose. The divergence of v in spherical coordinates isn't just dv r dr plus dv theta d theta d theta plus dv phi d phi. Oh no, 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 no. It is equal to 1 over r squared times the partial with respect to r of r squared times v sub r plus 1 over r sine theta times the partial with respect to theta of sine theta times v phi, v theta, I meant to say v theta, sine theta v theta, plus 1 over r sine theta times the partial with respect to phi of v phi. Much messier than the corresponding expression in Cartesian coordinates, at which point students typically say, so why do we want to use spherical coordinates, Dr. Hartman? And the answer is that this complication is worth it when you're dealing with problems that have spherical symmetry. Because if you have a function which only depends on r, for example, well, then this is pretty easy to do because the phi derivative and the theta derivative are both 0, and you'd only have this piece to work with, not too bad, for example. Whereas if you're doing it in Cartesian coordinates, you have to put the function being of the square root of x squared plus y squared plus z squared. And you've got to take these funky x and y and z derivatives of the square root of x squared plus y squared plus z squared. So, you know, what if your function was sine of r or something like that? You know, so then you're taking the derivative of the sine of the square root of x squared plus y squared plus z squared. And icky. So even though this looks more complicated, for problems which have spherical symmetry, it's easier in general to do this than it is to put the function in terms of Cartesian coordinates and use the nice simple Cartesian expression for the derivatives on the nice complicated function written in terms of Cartesian coordinates. This still ends up being easier. And so, despite first appearances, spherical coordinates are in fact your friend. Curl V is 1 over r sine theta times the partial with respect to theta of sine theta v phi minus the partial with respect to phi of v theta times r hat plus 1 over r times the quantity 1 over sine theta times the partial with respect to phi of Vr minus the partial with respect to r of the quantity r d phi times theta hat plus one over r times the partial with respect to r of rb theta minus the partial with respect to theta of Vr times v hat. Well now, isn't that lovely? And the Laplacian of a scalar is given by, and boy is this ever important, seriously, is given by 1 over r squared partial with respect to r of r squared partial of f with respect to r plus 1 over r squared sine theta partial with respect to theta of sine theta partial of f with respect to theta plus 1 over r squared sine squared theta, second partial of f with respect to phi. The angular piece of that. If I factor out this 1 over r squared and just look at the angular piece of that, what other class might some of you have taken where that shows up prominently? Quantum mechanics, yes. That is related to the angular momentum operator. The orbital angular momentum operator is a constant times the radial part of the Laplacian. And you may recall that when you're finding the energy levels of hydrogen, for example, well, the energy operator, the momentum operator squared is h bar squared grad squared over 2m. So when Schrodinger solved the Schrodinger equation, I mean, he wasn't just starting from scratch. It was a well-studied problem in other contexts. The Laplacian was certainly a well-studied beast, and so he was using very well-known mathematics applied to the wave function of hydrogen in order to find out what the energies are. It's definitely not just beginning from the beginning there. Okay. Now, having cut our teeth on spherical coordinates, we're waiting for more. So let's have some cylindrical coordinates. And then, tempting as it might be, we won't do like elliptical coordinates, you know, where the surfaces are ellipses and so on and so forth. As much as I want to do that, we're just going to stick with spherical and cylindrical coordinates. So, with cylindrical coordinates, those are appropriate to problems which have cylindrical symmetry, right? And in cylindrical coordinates, what we do is we take our point, and now we say that instead of talking about one of the coordinates being its distance from the origin, we use one of the coordinates being its distance from the z-axis. And we're going to call that coordinate s. Most physicists, those are supposed to be valid, most physicists call that coordinate r. Your author says that leads people to confuse the r of cylindrical coordinates with the r of spherical coordinates, and so let's give it a new name, let's call it s. I'm actually okay with that. I think that's not a bad idea. So, s is the distance from the z-axis, but just be aware in most contexts you'll see that written as r. And then phi is, again, the angle between the projection of the line from the origin to the point in question on the xy plane. And now, instead of theta, we use z, and z is defined to be z. It's the same as it is in Cartesian coordinates. So our relations are that x is equal to s cos phi, which isn't too hard to see because s is also the length of the projection onto the xy plane there. And so therefore, making our right triangles here, then certainly x is just hypotenuse s times the cosine of phi. Y is hypotenuse s times the sine of phi. And the tricky one is z. To get z, we project z along the z-axis, and the result is z. So z is actually equal to z, it turns out in this case. Now, if we want the unit vectors, s hat sticks straight out away from the z-axis, and z hat is along the z direction, duh. And phi hat is along the phi direction, if you will. In other words, the direction as amuthally parallel to the xy plane, just as it is in spherical coordinates. It's the same phi hat that you have in spherical coordinates. And s hat is equal to cosine phi x hat plus sine phi y hat, and phi hat is equal to minus sine phi x hat plus cosine phi y hat. If you had mechanics, you look at that and say, holy crap, those are the components of the rotation matrix, not a coincidence. You're just rotating x and y or y vectors through an angle phi, so that takes the rotation matrix, so there it is, if you had mechanics. And z hat, another tricky one, is equal to z hat, it turns out, as a matter of fact. Line element same sort of argument we used in spherical coordinates. The line element is just going to be ds s hat in the phi hat direction. We'd be moving through a little angle d phi, and along an arc of length, along a radius s through an angle d phi, making a little arc which becomes a straight line as d phi goes to 0. S times d phi times phi hat, and z hat, dz z hat. And the rule for the volume element is always just that you multiply the three displacements by one another, because you'd be making a little r-par whose sides are the elementary displacements. So the volume element d tau will be the product of ds, s d phi, and dz. So you get s ds d phi dz for the volume element. And for the vector derivatives, the gradient, as long as your coordinate system has orthogonal unit vectors, the gradient you always get by just dividing by the line element components. And so the gradient of a scalar function in cylindrical coordinates is just partial of f with respect to s hat. You're just dividing by the change ds in for the s component, and then it's going to be 1 over s partial of f with respect to phi hat, and then just partial of f with respect to z hat. So again, once you know the line element, you got the volume element, you got the gradient. There's nothing tricky about those. On the other hand, when you talk about the more complicated vector derivatives, like div v, for example, well, then things get a bit trickier. It's 1 over s partial with respect to s of s ds plus 1 over s partial with respect to phi of d phi plus partial with respect to z of dz. And that's showing up because basically z is a Cartesian coordinate. It's also a cylindrical coordinate, so that piece looks the same. Curl of v, curl is always the most fun. The curl of v is 1 over s partial of z with respect to phi minus partial of phi with respect to z, s hat, plus partial of ds with respect to z minus partial of dz with respect to s, plus 1 over s times the quantity partial with respect to s of the quantity s dt minus partial with respect to phi of the s z hat. That's kind of fun. I like writing out complicated expressions sometimes. And the Laplacian is 1 over s partial with respect to s of s, partial of f with respect to s, plus 1 over s squared, second partial of f with respect to phi, plus, let's say, Cartesian coordinates. So for z, we just get the partial with respect to, second partial with respect to f. Z, with stop, second partial with respect to z of f, d squared f dz squared. Okay, any questions? All right, so of course I'll be sending you email with your next opportunity to achieve happiness and joy. And so next time too, we'll take the divergence of r hat over r squared in spherical coordinates. And then I'm going to say, haha, suckers, you did it in Cartesian coordinates in this homework. And it's much easier to do in spherical coordinates. So anyway, see you next time.